Welcome to Chemistry Lab. Today's lab, intermolecular forces and colligative properties. The strength of intermolecular forces determines how strongly molecules are attracted to their neighbors, and that has a lot to do with what phase you tend to find certain substances in. For example, if we think of liquids and their conversion to the gas phase, vaporization of liquids to gases. We know that in the gas phase, we can assume that the molecules are far apart from one another and are not even close enough to one another to attract one another. Whereas in the liquid phase, they are close to one another. There is attraction, active attraction going on between neighbors. So the stronger the attractions are, the more difficult it is to separate those molecules, and therefore the higher temperatures that are required to do so. We associate strong intermolecular forces with higher boiling points and higher melting points. It requires more energy to separate molecules from their neighbors. So in this lab, we're going to be looking at molecular structure and how that relates to molecular geometry, what we see in 3 dimensions, and then how that affects the nature of the intermolecular attractions that these molecules have to their neighbors. When we look at molecules that are alike and the attractions they have to their neighbors, for example, when we're looking at liquids converting to gases or solids converting to liquids, we're looking at neighbors that are alike. The main types of intermolecular forces that we're observing are these 3: hydrogen bonding, dipole-dipole, and London dispersion forces. I know you've been going over these in class, so I won't go through all of the detail here, but a quick summary is that with hydrogen bonding, you're looking at a particularly strong attraction between neighbors where you find a hydrogen that's connected to a particularly electronegative atom, typically nitrogen, oxygen, or fluorine. That creates a strong attraction between neighbors. Dipole-dipole, where you're looking at molecules that have dipoles being attracted to one another. The London dispersion forces, generally thought to be the weakest of the 3, but all substances have a London dispersion force. That is the effect of the electrons that are within the structure. You can kind of think of it in that at any given point in time, you might have more of those electrons on one side of that structure than the other, generating a small amount of polarity and an attraction between neighbors. An induced dipole, we often refer to that as. So in addition to looking at molecular structure and molecular geometry, you're going to be looking at charge distribution within the molecule. And that will help you relate this back to the strength of these intermolecular forces. In the last part of the lab, you'll be looking at colligative properties, specifically freezing point depression. Colligative properties are properties of a solution that depend only on the amount of solute dissolved in the solvent. And in the case of freezing point depression, we're looking at the freezing point of pure water, which should be 0 degrees Celsius, and the freezing point of a solution. If you add salt to water, then the freezing point of that solution should be lower than the freezing point of pure water. Remember, in the case of water, we have the bent molecular geometry of water, and then the hydrogen bonding that occurs in water molecules. These water molecules tend to line themselves up so that the hydrogen bonding regions become more active, and you get this nice regular zigzag pattern of water molecules that we associate with crystal structure in the solid phase, right? A beautiful ice crystal. Has a lot of structure to it that we see here in the molecular level as well. But if you add salt to this, the ions somewhat disrupt this structure, and That means that we have to remove even more energy in order to achieve freezing, which means that the freezing point of a solution is always lower than that of the pure solvent. So in the last problem in the lab, you'll be looking at the equation that relates that. The difference in freezing point between the pure solvent, water, and the solution is the delta T. It is equal to I, which is the Van 't Hoff factor, which is the number of ions that are produced by the compound, or the number of units that are present. If it's an ionic compound, it's the number of ions, times a constant for water, which is in your lab manual, times M, which represents molality of the solution. And molality is equal to moles of solute per kilogram of solvent. In using these equations and the equation for the molar mass, or just the units of molar mass, which by now you know the units of molar mass are grams per mole, in the given problem at the end of the lab, you should be able to manipulate these equations to find the molar mass of the given compound. I believe that's all you need for this lab. Have a great lab.